All right. So, morning everyone to this last YP webinar for 2025. We are fortunate to have Dr. Eirini Eleni Tsiropoulou to give us a talk on her research that she is doing titled Heliocom, Architecting the Next Generation of Resilient and Autonomous Solar Fields. Dr. Tsiropoulou is an associate professor with the School of Electrical, Computer and Energy Engineering at Arizona State University. She obtained her diploma in electrical engineering from NTUA Athens in 2008. She has an MBA as well, and then following up, she has a PhD from NTUA in 2014. Her MBA was in 2010. She works in the area of game theory, reinforcement learning for decision making in complex systems. She has won numerous best paper awards. She has received multiple awards from NSF, including the Early Career Award from the IEEE Communications Society. She was identified as one of the top 10 rising stars of 2017 in the communications and networking field. Her research is funded by the Department of Energy, NSF, as well as the industry. She's also active in the community. She's an area editor for the IEEE transactions on green communications and networking, associate editor for IEEE transactions on machine learning in communications and networking, and several other IEEE transactions, papers, journals, as well as magazines. She's also a co-chair of the N2 Women community. So thank you, Eirini, for agreeing to give this talk. The floor is yours.
Thank you, Anamitra. Thank you for the kind introduction, and thank you everyone for joining today. It's actually a great pleasure to give a webinar for young professionals. So today I will present one part of the research performed in the lab. As Anamitra gave a kind introduction, the lab is mainly working on decision-making in complex systems. And one of those complex systems are the systems of heliostats, where practically energy is harvested / created, I should say, from the sun in order to be transformed into electricity and support our households as well as industrial settings. So I slightly changed a little bit the title of the presentation, most probably to do it a little bit catchier. So the main work that we are doing in concentrated solar power fields is that my lab has invented the first wireless communication system to support those fields and go away from the traditional wired technology that is mainly used nowadays, vastly actually in commercial CSP fields. So with that, what I will discuss today is mainly how we can use the wireless technology in order to overcome costs, security aspects, as well as operational obstacles that are existing in concentrated solar power fields. And to do that, I will introduce our technology invented in our lab, the Heliocom technology, which is mainly based on network function virtualization and software-defined networks, as well as artificial intelligence techniques to be able to give the autonomy to the nodes within the field to self-organize themselves. And on top of that, some game theoretic approaches in order to deal with the resource management of communication resources in order to make the field fully operational and fully autonomous in terms of controls and communications. So on top of that, after we set up the system, we will discuss how the system can be affected by seasonal dynamics, but also how we can make the system secure to different types of attacks. And mainly today we are going to focus on the jamming attacks, which are very common in concentrated solar power fields. At the end, I will present you some real testing that has been performed at Sandia National Laboratories, where a testing facility of 218 heliostats exists there, and we have some realistic data sets, and also those are publicly available. And we will conclude with some future steps that we have in mind, and they are currently being implemented in my lab, the Performance and Resource Optimization in Networks Lab. So without taking more time, let's understand, first of all, what is the major challenge in concentrated solar power fields that we are trying to address with this technology. So the existing fields are mainly depending on rigid hardware-dependent architectures, mainly wired. which have several challenges, mainly in terms of high installation cost, but also very high maintenance cost after you install all those wires in these fields. That you should keep in mind that those fields are of huge sizes, so they have kilometers of radius from the central tower where the energy is being created, actually transformed from thermal energy to electricity. So given the size of those fields and given the scalability issues that are related with those fields in terms of controlling them, there is a real need of an autonomous system where practically those heliostats, they can be controlled in an automated manner. And why controlling the heliostats is so important, we should keep in mind that the heliostats follow the sun with a milliradians accuracy, which practically means that we need the real-time control over those nodes. So commands need to be sent from the central station where all the computing is taking place and be broadcasted or specifically unicasted to each node in the field. So each node knows in a real time how it should move in order to optimally follow the sun. And someone would think that optimally following the sun is good in order to maximize the energy exploitation. However, that's not the only point, because in a heliostat field, if the heliostats are not optimally controlled, there is a danger that the field can be we can have catastrophic events within the field, because if all the heliostats are pointing in a wrong way within the field, they can even end up setting the tower on fire. So practically we have a total damage within the field, which is millions of investment in a commercial field. So it's not only not to lose money because of optimal energy harvesting, but also make sure that you don't damage the field while it is operating. So this is a fundamental reason why we care so much of optimally controlling the heliostats in the field, and why we are so much interested in this technology. I should say that this technology is very well known and very well incorporated within the smart grid networks of countries like China, Israel, Spain. There are some initial attempts made in the United States. We have some commercial fields in Nevada, in the boundaries actually of Nevada with California, the Ivampa field. It's a huge field with 350,000 nodes and 3 central stations with the towers. So we understand that there is a real need for increased energy. So we need to supply the customers with increased energy demand. So the renewable solutions, they can be a very good potential aspect that can cover those demands. But also, when we study the renewable energy resources, we need to make sure that we minimize their environmental footprint. So we maximize the energy exploitation, but at the same time, we do not harm the environment. And the environment can be harmed in several manners. So, for example, when you intervene so much within the installation, so for example, with all the cabling of the wire technology, that means that when the field after several years, becomes obsolete and the area needs to be renovated, then obviously the more infrastructure you have in the field, the worse is your environmental footprint within that area. So to address those challenges of increased energy demand and decreasing practically the damage or the impact that we have on the environment, the wireless communication technology supporting concentrated solar power field can be a good candidate, mainly because it's a much cheaper technology compared to and I have some numbers to present, compared to the wire technology, but also it can scale up in very large fields. Because we don't have the need of, trenching all that cable within the field and maintaining as well. It's not only the installation, but it's also the maintenance. So there is an initial attempt to turn the concentrated solar power fields into operating in a wireless manner. There are some initial attempts in Israel by Bright Source Technology, but also in China. However, those technologies, those existing technologies, they mainly reiterate what was well known in 90s wireless cellular networks of frequency reusability, where they are using access points within the field. So really the infrastructure is not that decreased. However, there is an initial attempt for wireless communications. So to give you some numbers, why the wireless communication technology can improve the operation of CSP fields. First of all, a main aspect is the cost. So we have done a techno-economics analysis for some indicative heliostats, which are typical heliostats in commercial fields, the 20 square meter heliostats. The cost for just installing the wired infrastructure for one heliostat, it's about $400 per heliostat, while the corresponding cost of plugging in, practically attaching actually, a wireless module to the heliostat with a small photovoltaic embedded on the wireless module, the cost is about $100 for one heliostat. So that means that if we take the simple example of Ivanpah field here in the United States, we discuss about the cost reduction of 75%, and in real numbers, it's multi-million of cost reduction, because as I said, those fields are really huge fields in terms of heliostats. Also, this is the aspect of what I discussed is the aspect of the infrastructure, but then we go to the aspect of the maintenance, where the wire technology, it needs regular maintenance of the wire that is in the field, because obviously it can go bad over the years. While on the other hand, the wireless technology, given that it has reduced physical infrastructure, the worst case scenario is that we will need after some years to replace the whole wireless module, which, as I said, it's about $100 cost. Now, moving from the cost to the scalability aspect, the wireless technology can enable us to scale in very large fields without the need of having wired communication within the field. However, I should highlight that the wireless technology, given that it can suffer from fading and noise compared to the wired one, it's challenging in terms of its reliability. So when we design a wireless network, we need to make sure that it's sufficiently reliable in order to support the industrial application of CSP. And why we care so much about the reliability, because obviously if we lose control over the nodes, on one hand, we lose part of the harvested energy. So I have given here some numbers regarding 1 hour of downtime in Ivanpah field. That costs approximately $12,000. Just 1 hour of having the field disoriented. And obviously you understand that this is a cost, but then as I said earlier, if we lose control over the heliostats, so for example, if we have malicious actions within the field, the heliostats can end up burning the central station. So we discuss about a holistic catastrophe within the field. So that means a multi-million damage. So the challenge that we have identified in our lab 3 years almost ago is that we need to design a system, a wireless system that is reliable. It's optimized in terms of its operation, meaning optimized resource management within the field, like the spectrum, the transmission power of the nodes, and we make sure that it is fully autonomous in its operation. So that can make it easily adopted by stakeholders that want to deploy this technology. So our design is based on the concepts of network function virtualization, where practically several functions that need to take place within the wireless system, they are organized in a virtualized manner. And those functions can be the routing of information within the field, or the dynamic spectrum management to allow all those nodes to transmit simultaneously towards the receiver. And to achieve the autonomy of the field, we are adopting software-defined networking concepts where practically allow us to reprogram in a real-time manner the operation of the field, the wireless communication aspects, so we can guarantee smooth and reliable connectivity with the central station. So the vision that we have introduced is that we move away from the rigid control logic that is based solely on hardware-based implementations and infrastructures, even from the initial attempts that have been made in China and Israel, where practically they are deploying routers and access points within the field in order to support this massive connectivity of the thousands of connected nodes. And we are going a layer up, where practically we are implementing a software-defined networking technology, where we virtualize the fundamental functions that need to take place in the field. And practically we just allow the heliostats to operate with simple commands in order to support their autonomy. So putting together those pieces, our lab has a patented technology, the Heliocom technology, which practically supports the programmable solar control. So practically we can program the wireless nodes within the field in a real-time manner by using the software-defined technology that is taking place at the central station, and practically sending control commands to the nodes, where the nodes afterwards have the autonomy by themselves to adapt by sensing their environment to their optimal operation. And when I say optimal operation, I mean what frequency they are going to use in order to transmit, how much will be their transmission power in order not to exhaust their battery. Remember that each wireless node has a small photovoltaic on it, and it has a rechargeable battery. And we have nodes like that in our lab. I'm going to show some results later. And so the nodes have the intelligence of managing the spectrum, controlling their own transmission power, performing an interference-aware routing, so each node knows how to route its information in an autonomous manner in order to reach the central station. And the nodes are self-organized into clusters within the field by following the concepts of non-orthogonal multiple access technique and successive interference cancellation technique in order to support the scalability. So in layman's word, that means that each node, when multiple actually nodes transmit to the same cluster head, they are self-organized in a manner that when the cluster head receives this information, there's not a chaos, but the cluster head can practically decode its individual information and then forward it all the way through routing to the central station. So the fundamental wireless technology that we have used is the integrated access and backhaul technology that practically allows the dynamic spectrum management between the access network, between the cluster head and the cluster nodes, and the backhaul network, which is the wireless multi-hop communication all the way to the central station. And this is a fundamental difference compared to existing wireless attempts in CSP, when instead of having a wireless communication multi-hop manner at the backhaul of the network, they were using access points that they were practically, using wires in order to spread those access points in the field, which this still was keeping the infrastructure cost quite high. So putting together those components, let's start analyzing the operation of each one of them, given this overall vision that we have about self-optimizing the overall network of CSP in order to support the intelligent energy collection within the field based on the software-defined technology of all those operations that I discussed. So those fields that you see on the right, they are indicative commercial CSP fields that exist around the world. So this specific field has approximately 44,000 nodes being connected to one tower. The tower, as you can see, is in the center of the field, and the heliostats are spread around it. So the multiple colors that you observe are practically the different frequencies that are allocated to each area within the field. And then nodes that are that belong to the same, they are utilizing actually the same frequency. They are self-organized within a cluster, and they are those nodes that you see. And then the nodes that are belonging to the same cluster, they are transmitting their information to the cluster head, and then the cluster head in a multi-hop manner by utilizing other cluster heads that transmit at the same frequency forwards the information all the way to the central station. So why it is important the central station to collect this information? The reason is that the central station can have real control over information like the azimuth and elevation of the heliostat. So if the central station needs to auto-calibrate the heliostats, then it can send commands to them, again in a wireless manner, so the heliostats can self-calibrate in an autonomous manner. Now, I discussed this concept of clustering. Let's see how this clustering is performed. So we said that we cluster together nodes that they operate at the same frequency, but the question is, we have so many nodes out there, so how we will create those clusters in order not to suffer from interference among each other and from interference from other clusters that transmit simultaneously at the same frequency. So the main idea that we are using is the non-orthogonal multiple access technique. This allows multiple nodes to transmit at the same frequency, and at the same time, the successive interference cancellation technique at the receiver, which if you can see in a simple diagram, that means that if we have selected the cluster head, and the cluster head is selected practically by a centrality metric in terms of the channel gain conditions, when we start adding potential cluster nodes within the cluster, we need to make sure that they obey the successive interference cancellation technique. That means that their signals are spatially distributed in a way that when the signals are received at the receiver, the minimum signal to noise ratio, the minimum signal to interference plus noise ratio is guaranteed. So that means that all the received signals are not sensed as noise at the receiver, but we still capture their spatial diversity. And first, we emphasize on building the clusters that are supporting closed-loop auto-calibration. And closed-loop auto-calibration means that within the field, the CSP engineers, in order to auto-calibrate a batch of heliostats, what they are doing is that they are taking them offline. They are making them to point to a focal point, and then they measure what is a counting error. So they send commands every 250 milliseconds in order for the heliostats to auto-calibrate to the correct pointing angle. So obviously this operation is control heavy. So there is a lot of controlling commands that they need to be sent to the heliostats. So that's why we give priority in the sense that we respect stricter signal to interference plus noise ratio constraints to make sure that we don't lose any information. And then the rest of the we continue with clustering the rest of the heliostats that perform non-closed loop auto-calibration, which is practically regular commands that we want to send to the heliostats. For example, we want to request to report the azimuth and elevation angle, or we want to request to report some sensing information. So for example, temperature level, soiling level, etc., based on other sensors that are attached onto the heliostat. So that's how we perform the clustering. Now, this technique that I describe in layman's word is performed by using an artificial intelligence approach. So practically each heliostat within the field is acting as a reinforcement learning agent, senses the different components. So for example, the interference, the received signal strength, the SINR, the interference stemming from the rest of the heliostats. And we have designed a reward function that practically allows each heliostat acting as a reinforcement learning agent to decide which is the optimal cluster head to be connected to in order to satisfy all those constraints that we discussed earlier. So after the clustering is performed, now the heliostats know to whom they should talk within the field in order to reach all the way to the central station. So then the next step is how they communicate. So what should be their transmission power levels? So to do that, we formulate this problem as a non-cooperative game theoretic approach, where practically we implement a very low complexity best response algorithm that runs on the heliostat in order for the heliostat to decide what is the optimal transmission power, considering what are the strategies of the rest of the heliostats within the field, not only the heliostats that belong to the same cluster, but also other clusters that are transmitting at the same frequency. So obviously this is a non-cooperative game because each heliostat tries to satisfy its communication with the cluster head and all the way to the central station, while competing for spectrum and with respect to interference within the field. So this best response algorithm is a very low complexity algorithm that can be implemented on the heliostats, and we have implemented that in reality within our lab, as I will present in a bit. So here are some indicative results from our experiments. I should give a hint that in our lab, we have a real emulated concentrated solar power field. And I say emulated because we don't have the heliostats, but we have a real field. It's a almost 10 acres field in Mesa, in the Polytechnic campus, where we have 2,000 wireless nodes spread within the field, emulating a real CSP environment. And the only thing that we are missing are the real heliostats. So we have some sticks where the wireless nodes are on the sticks, so we can emulate the height of the heliostat. So here are some results that we have collected from a set of 7,683 heliostats. I should say that those results are simulation-based results, but in a bit I'm going to show you also some results from the real field. So we have run this testing for a duration of 2 years in order to capture the environmental effect during the different seasons. And the results demonstrate the latency that is achieved in the closed loop and non-closed loop autocalibration. And our target metric when we discuss with CSP engineers for the closed loop autocalibration is that our latency should remain below 250 milliseconds for the real control operation. And for the non-closed loop autocalibration, we can be below 10 seconds, which we can observe that in both cases, the results are achieving this goal. We have demonstrated the maximum latency because this is the worst case scenario. So we want to see what's the worst effect within the field. Also, I should point that those zigzags that you observe are stemming from environmental conditions. And the reason is that the channel gain conditions of the wireless medium, they are affected by different events, especially by the weather events. Then we have captured the energy efficiency of the access nodes and the cluster heads in the access nodes and the cluster heads in the case of closed loop and non-closed loop autocalibration. And we care about the energy efficiency because it's practically how much data you can transmit with one cost of energy unit. So we observe that for the size of the data that we are discussing, which is about 95 bytes every 250 milliseconds, the energy efficiency remains quite high. And obviously we see that the energy efficiency in the case of the CLA, it's quite improved. And the reason is that, as I said earlier, we give higher priority, and the higher priority is given by allocating a larger part of the spectrum. We have compared our solution compared to the initial approach that has been implemented in Israel by utilizing mainly the access points in the field. And they are using the concept of segmentation. So they create segments within the field, and each segment has an access point associated with it, where approximately 100 heliostats are connected to each access point. And we have compared with respect to the data rate. So we care about making sure that the information is received in a fast manner at the central station. So the comparison is done both for the non-closed loop autocalibration and the closed loop autocalibration for the access nodes and the heliostat and the cluster head, and we observe that the data rate is quite improved. The reason for that, it's not really magic, but the reason for that is the dynamic spectrum management that we are performing and the non-orthogonal multiple access technique that is used, which practically allows the system to scale in a bigger manner. That means that for the same scale of a system, for the same spectrum band, our system can accommodate more nodes. So that means that if we discuss about the same number of nodes, we can obviously achieve a higher data rate. Now, moving forward, after implementing our initial version of the Heliocomp technology, we wanted to test how this technology is affected by the seasonal dynamics. And why we care about that? We care about that because the CSP engineers, when they operate a real field, they need to auto-calibrate it in a periodic manner. So they need to know how much time it takes for a whole field to be auto-calibrated to make sure that they optimize the energy harvesting. And that was our main study that we did here. So how the communication and respectively the control part is affected by the seasonal dynamics. And obviously the seasonal dynamics affect the operation of the field because as the sun, it follows different moving patterns during the year. So it has a different pointing factor, let's say, how it points towards the heliostats. So that reflects on the channel gain conditions of the heliostats. And obviously in the winter, where the sun is not that vertical to the heliostats, then the communication environment will be much more affected in terms of operating within the field. So after experiments that we performed in the field by utilizing the Sandia National Labs infrastructure, we tested how much time it takes for us to pass the whole field during the spring, the summer, the fall, and the winter period in terms of auto-calibrating the whole field. And we can see that actually based on the data that we collected from Sandia for 218 nodes, we emulated the data for the same field of the 7,683 nodes. And we observed that it takes about 6 days, which is the worst case scenario during the winter, to auto-calibrate the whole field. So this is an indicative factor for the CSP engineers of how much time it needs for auto-calibration. Then, given that we ran those experiments, we wanted to see, okay, why it takes more during the different time periods or year periods. So we checked the average latency of the cluster heads and the access nodes during the year, and we observed a persistent lower latency observed during the sunny months, which are practically the summer months. So this is an indication of why it takes longer during the winter, but also someone should point that the spring and the summer and the spring and the fall periods, they don't have substantial difference given the size of the field that we studied. But obviously when we go in much larger fields, this difference will be larger as compared to the summer period. But this technology is out there for whoever wants to do a quick simulation for their field to see how much time it takes for the closed loop auto-calibration to be performed by passing the whole field. Now, moving forward, one major challenge that came up with the wireless technology is cybersecurity, is the cybersecurity attacks. And this is not an unrealistic assumption. Actually, a cybersecurity attack was performed a couple of years ago in the concentrated solar power field of Ashalim in Israel, where practically the whole field went down for some good time of period. And this attack was stemming from a jamming attack. Jamming attacks are very common in concentrated solar power fields because those fields are by nature isolated. So very easily someone can just drive a truck next to the field, start jamming the whole field by transmitting with very high power. So the whole field becomes non-operational in case that is operating in a wireless manner. So how we can safeguard the field from such type of attack without having very huge expenditure for physical type of security, like, have guards within the field, etc., etc. So this is part of a patented technology here at Arizona State University, where practically the main idea is that we are using a machine learning approach by having all the data that we have collected from the Proton testbed that I discussed earlier at MESA, So we have all that data regarding the wireless channel conditions in a realistic commercial concentrated solar power field. And we want to study the different types of malicious attacks. And our initial study focused on the jamming attacks. So in the jamming attacks, what happens is that we have some malicious users within the field that they start transmitting with very high power. So that increases the interference and increases a domino effect to the other nodes that they also try to transmit with high power. So then the interference levels are prohibiting in order for their signals to be received and decoded by the receiver. So in order to detect the jammer or jammers within the field, we embedded the hypothesis testing within the machine learning model that we have. And the hypothesis testing, practically what it does is that when we initially set up the field, we run some measurements where we know what is the regular pattern, communication pattern within the field in terms of received signal strength. And then we have a corresponding elasticity factor, which is practically the gamma factor that you see on the slide, where we can have some elasticity in terms of detecting or not a potential compromised attack within the field, which can be a jamming attack where practically the received signal strength starts increasing dramatically. So we have run several experiments based on collected data where we have a denial of service attack without ejection, with no ejection. So practically we just detect the node, but we don't eject the node. And corresponding results where practically we eject the node from the field, and the node is ejected practically by performing a triangulation technique in order to pinpoint exactly where the malicious node or nodes are in the field. And we have some experiments where we have coordinated distributed denial of service attacks with multiple nodes within the field. And practically what we observe is we want to capture the quality of communication through the mean squared error, where practically we know what is the expected signal to be received, and then what we really receive and how far away we are. So we observe that obviously when we eject the nodes within the field and we have some success rate, which obviously it's a function, as we will see, of the elasticity factor that I presented earlier, we can achieve very low mean square error values, and very close to the benign case, which is the good case. So we have run also experiments, again, with single or multiple jammers within the field and with different detection thresholds, which are the elasticity thresholds that we discussed earlier, with respect to the with the achieved quality of communication as captured by the average mean squared error. And obviously we observe that when we have multiple jammers within the field, the mean square error starts deteriorating, and it's a matter of optimally tuning the detection threshold in order to detect successfully the nodes. However, here I should put an asterisk, as I think we have some results down the field, that depending on the detection threshold, we can have false alarms. So we have done a sensitivity analysis about setting up the detection threshold. To do that, we have performed some testing by utilizing practically the topology of Sandia National Labs, practically the real topology of the National Solar Thermal Test Facility at New Mexico, where we want practically to, what we did is we launched our technology there, and we wanted to detect the different jammers that are in the field. So we ran scenarios of distributed denial of service attack and simple single attack as a function of the detection threshold. And we observed that obviously the stricter we are with respect to the detection threshold, more accurately we can detect the jammers. However, we have scenarios of false alarms where practically just a worse channel gain condition triggered the nodes to transmit with higher transmission power, but this is not a real malicious attack within the field. And I should highlight for accuracy that though this testing has been performed here at the ASU facility by replicating exactly the topology that we have at Sandia National Labs. So we have done also a detailed analysis, sensitivity analysis, considering the detection threshold and how many jammers we have within the field in a percentage manner. So, and the results are very similar to what we observed earlier, but now we do that also with respect to a varying, increasing number of jammers within the field. The initial number of jammers was, if I recall correctly, 4 in this graph. And then percentage-wise, we increased them. Now, to start concluding what we discussed today, so we in the lab, we have developed several technologies that support the concentrated solar power fields, mainly focusing on the wireless aspects and the fully autonomous operation of the field in terms of wireless communications, but also in terms of cybersecurity, initially focusing on jamming attacks. So our technology practically can achieve a 75% cost reduction compared to the wired infrastructure. And I highlight the word infrastructure because additional cost reduction comes from the maintenance. This technology, both the wireless communication, the cybersecurity technology for CSP, they are patented technologies available for stakeholders. And our vision is to extend our work by focusing on improvements of our technology, mainly using deep reinforcement learning techniques in order to further optimize the operation of the field in terms of communication. So, for example, we want, as the hardware becomes improves over the years. So what does that mean? That I can have a wireless module that has also a more powerful microcontroller on it that can run more advanced algorithms than the simplistic reinforcement learning algorithms that we currently have. We want to invest into that. Currently in the lab, we are doing some testing with software-defined radios, where practically those algorithms can be embedded on the software-defined radio for testing purposes. We want to extend the work that we are doing on the cybersecurity aspects for dealing with backdoor attacks within the field. So practically when someone wants to take control over the field and presenting a completely different picture of how the field is really operating right now. But also given that in different countries around the world, though the CSP fields are not only constructed by heliostats, but also they embed hybrid renewable resources. Like, for example, they have the heliostats, they have photovoltaics, they have wind turbines. So we want to implement a holistic wireless system that can support those hybrid renewable systems, which are very common in commercial fields. Currently in the lab, which is practically a goal that has been achieved, our wireless nodes are fully autonomous in terms of energy consumption. So they have a small photovoltaic embedded on them, so they can be, they can fully operate literally forever, because with experiments that we have done, we can see that the algorithms that we have embedded on the wireless nodes can allow the nodes to run 7 days in a row without harvesting zero energy from the sun. So in worst case scenarios that we have cloudy days. Now, we are extending our technology to target other types of markets, especially focusing on smart grid, managing different types of distributed energy resources, different DRs, like especially we are working a lot with electric vehicles within our lab, but also the proposed wireless technology can be adopted in several types of industrial Internet of Things industries, like smart factories, agriculture, but also aerospace technology, where practically currently we are working with several aerospace companies who have interest in this technology. And different autonomous systems, because as I said at the beginning, our lab is focusing on different types of complex systems and decision-making into them. So currently the lab also focuses on low altitude economy, which is a new technology in order to support different types of applications within smart cities, like traffic management, surveillance, delivery of goods, etc., etc. So our technology is not really tailored or personalized to the CSP. It has already found applications in different fields. With that, I want to conclude the talk with some publications that have been concluded out of this project, which was also some patents. Here I have the patent that has, it's already available out there. There is also another patent coming from ASU. This work was very kindly sponsored, is very kindly sponsored actually by the Department of Energy, and 3 of my senior PhD students are working on this research area. Sadman, Aisa, and Dipanchan. Sadman and Aisa are graduating in spring semester. They are out there in the market, guys. So if anyone has interest, you're more than welcome to contact them. And with that, I would like to thank you and open the floor for questions.